I'm working for Electronic Arts, or EA. We are a gaming company. We are producing a lot of beautiful games every year. So those games are generating a lot of data, terabytes of data every day. And we are using this data to derive deeper insights into the games, how to improve the games and also improve the engagement of the players. So at EA, we have, instead of having 4 seasons a year, we have 2 seasons, game launch or non-game launch. Every day, we don't have 24 hours. Instead, we have only 2 hours, peak hour and off hour. So at different times, the data traffic actually fluctuates a lot. So for performance and cost reasons, we have to be able to scale up and down the computer resources very quickly and also frequently. So very naturally, we are building our big data infrastructure in the cloud. Roughly, the tech stack is divided into 3 layers. At the bottom, infrastructure and the platforms and applications, one sitting on top of other. So there are some general problems across industries in the cloud-based tech stack. So we have observed varying degrees of automation across different layers. So at the infrastructure layer, the service providers like Amazon is doing a great job. So everything is pretty much automated. So as customers, we're able to launch or terminate hundreds of instances in just a few seconds and with a few clicks. However, the platforms and the applications are not achieving the same level of automation. So most of those are still manually configured and managed. So this problem is causing a lot of operational costs in the platforms and the applications. So first, the lack of automation in these systems make it hard to scale up and down when we need. And the mismatch of automation across different layers makes it very difficult to keep everything in sync. So the consequence is that you're observing a lot of operational overhead, a lot of alerts. So, and the engineers are busy just resolving the alerts and solve the operation challenges. They don't have much time to do dev and deep innovation. So to solve these problems, we have to either redesign or upgrade the systems in a more cloud-native architecture, or we can leverage existing orchestration technologies to make life easier. So in this talk, I'm going to overview 2 projects I have been involved since I joined EA last summer. One is the monitoring system, another is data platforms. And we can see how the orchestration technologies can help us solve the scaling problems and the operation problems. Can you imagine a monitoring system that sends you thousands of alerts every day? So the life of the operations team is like a busy mommy, having a miserable life, just sitting on 1,000 crying babies. Some babies are crying because they're hungry. Some babies are just crying for fun or for attention. You cannot really tell. So let's take a deeper look how a monitoring system is roughly like. At the bottom level, we have metrics sensors deployed on all the machines, collecting metrics such as CPU, memory, and disk usage. And at the next level, we have the metrics aggregator that collects all the metrics in one box and make it easier for you to query. And at the top level, there's alerts generator that query the metrics and check conditions. They send you alerts once some condition is satisfied. So all those different components, you need different configurations. For the metrics sensors, you need to know what metrics to collect and where to send the metrics to. For the matrix aggregators, you need to know from which machines to collect the matrix. And for the alerts generator, you have to know which machines runs what, and what kind of health check you should perform, and how to trigger the alerts. So we can observe a mismatch of automation across different layers that are causing a lot of operation problems. The monitoring components, on one hand, they are manually configured and managed. There's almost no automation at all. At the infrastructure level, everything is fully automated. We can just issue an API call. We can launch a lot of machines or terminate the machines right away. So this mismatch makes it very hard to keep the configurations up to date. So the consequence is you see a lot of false alerts, but at the same time, many of the new resources are not monitored at all. You don't know what's going on, and until something crashes and they have a major outage. So the solution to solve this problem, we started a project called Monitoring as Code last 1 year from now. So actually, the key insight in this project, we introduced an extra layer called configuration orchestration. So basically, this layer keeps the monitoring configurations in sync with the hardware status. And we're not modifying the underlying monitoring components at all. So it sounds like a sort of a middleware. So to dive a little bit deeper into the monitoring as code project. So roughly, at the center of this project is some automatic configuration generators. So from AWS, we get the host map, latest host map. That's roughly which machines are running in your cluster and which machines runs what. And we also input some specifications like how the monitoring components are wired, how these components are wired. And we need a library of methods to tell us what to check, how to check, perform health check, and trigger conditions. And the other input is we need a specification from the cluster owners, what to check for each cluster. So taking all this input together, we automatically generate configurations for alerts generator, for matrix collector, aggregator, and matrix sensors. And then any change you make to those configurations, or any change you make to the machines, your add machine, terminate machines, then any change will trigger the CI/CD pipeline. Everything will be treated as source code, the same as software code. And all the changes will be automatically deployed by the CI/CD pipelines to the underlying configuration, to the underlying monitoring components. So to summarize what this project does, so first we are managing all the monitoring configurations in one GitLab project. We impose standard configurations on the configuration files such that all the configurations can be automatically generated. And the configurations are treated the same way as the software code. They are also first-class citizen. And all the updates we make, they are reviewed, and everything is traceable. And all the changes will be automatically deployed by CI/CD pipelines. So essentially, this is just adding an orchestration layer on top of the monitoring components without modifying the source code of any of those components. It's transparent. So to measure the impact of this project, in beginning of the year, when before we deploy our project, we were receiving above 1,000 alerts every day. So this actually stressed out the infrastructure team. And then after the first major upgrade on one big cluster, production cluster, we see half of the alerts were gone. And then we experienced several iterations until end of April, after all the clusters are cleaned up and with our solution deployed. We see that the number of alerts dropped to about 100 per day. And then after a few more polishings, since the summer, this number was further reduced to about a couple of dozens alerts every day. With this small number, then even one single engineer can take care of it, and then the rest of the team is freed to do some deeper innovation. So hence, we have the second project, data platforms. So this is the current architecture of our data platforms. Roughly, we have two clusters. One is called Ocean, and one is called Pond. They're handling different workloads. Ocean is designed to handle internal customer ETL jobs. And Pond is designed to handle external customer and analytics ad hoc queries. So these two clusters are built on a joint data from the persistent storage provided by Amazon S3. But Ocean is built on HDFS, and Pond is built directly draw data from S3. So to see the problems more clearly, let's do a deep dive into the two clusters. So on the Ocean side, they are running internal ETL jobs. Actually, we have 2,000 to 3,000 ETL jobs running every day. So we only cache a few days of recent data in HDFS. The ETL jobs read and write on HDFS, take input tables and do transformation and write the new tables back to HDFS. And so we also need to back up the data to S3 for persistent storage. And then at the same time, we have to update the analytics cluster of availability of new data so that they can be analyzed and queried. So Ocean is more like a legacy tech stack. We are using, everything is built on top of Hadoop, Hive, Woozy. Those are pretty classic stack. So you notice there are two meta stores, one in each cluster. This is because in Pond, we're running external customer workloads. These are basically analytics in ad hoc queries and also some AI workloads. So they have to process the entire history of data. So that's why they directly draw data from S3. So for the end customers, sometimes they fear, oh, I have to run this query periodically. So we provide a lightweight mechanism called a self-serve system, so that they can turn some of the queries into a lightweight ETL jobs. So as a result, some of the analytic ETL jobs have dependency with the regular ETL jobs. Some upstream is on the other cluster, and the downstream is also on the other cluster. So you can see, because the two clusters are running on different storage, one is running HDFS, another one is directed on S3. So they have a different namespace or address space. And so we have to set up two Hive metastores. Another thing I need to point out is that we are also experimenting some more recent technologies on Pond, like auto-scaling group, Kubernetes, and Presto. So Pond has mixed legacy and modern tech stacks. This actually added to the complexity of the entire data platform. So there are a few main pain points that we have to address moving forward. First is we have to maintain and operate two clusters. The two clusters have many duplicate functions, like even the Hadoop Hive stack. So we want to consolidate those to minimize the operational cost. And the second point is Hadoop was not designed for scale. It's very difficult to scale up and down at the speed that we need for our business. You can scale up and down, but it can take weeks or a long time to do. But we expect minutes or even seconds. The third pain point is HDFS is used in the Ocean cluster for cache. But HDFS was not really designed for caching purposes. Then we have to implement our very complex custom code to do data backup, purge, retention, and loading. Those are actually very basic functions provided by a specialized cache service. We're reinventing the wheel, right? And the fourth problem is the address space is fragmented. We're using HDFS for ETL jobs. It only caches recent data. And we're using S3 for analytic jobs. Those are potentially, you have to work on the entire data set. So that's why we need to maintain 2 half meta stores, one for ETL and one for analytic workloads to keep them separated. But as a result, we have to perform very complex synchronization between jobs in different clusters and also between the meta stores. So to solve all these problems together, we started the Data Platform 2.0 initiative recently. Actually, we started from the summer and have been building POCs on this. So in this initiative, we consolidate the 2 clusters for different purposes. They could just be running in one cluster. Certainly, we can have different subclusters like Yarn and Presto. In fact, matter of fact, we have more than 12 Presto clusters for the time being, and this number is growing. Second is we're using CI/CD and Kubernetes, etc., new technologies to automatically deploy and scale all the computer resources. In particular, we're trying to implement auto scaling of Yarn cluster in addition to Presto. We already done the Presto part. And we are using a data orchestration. We introduced a data orchestration layer between the compute cluster and the underlying persistent storage. Specifically, it's Alluxio. So you can see that this is sort of providing a unified address space that can turn all the compute resources working on the same abstract storage layer. So we can see some clear benefits in using data orchestration here. For the analytics workloads, we are using Presto together with Alluxio. This actually is a basic use case. We use caching for better performance. We haven't done evaluation yet, but you can hear similar stories from other talks in the same conference. And for the ETL workloads, we are using Alluxio to replace HDFS. Alluxio is able to provide a specialized cache service. So it can automatically back up, purge, and load data for us. We no longer need to worry if the data is in our cache or not. It just handled transparently to your application. And Alluxio also provides one unified address space. This simplifies the synchronizations between jobs and the meta stores. So as a result, it becomes much easier to scale up and down the cluster, and we can automatically manage the computer resources. So as far as we can see, there are significant architectural benefits, but there was a concern. After replacing HDFS with Alluxio, are we going to lose performance? So the answer is negative. We have built POCs throughout the summer and did some preliminary evaluation. So basically, we are trying to compare the performance of Alluxio against HDFS. We set up everything such that they are equal in hardware configurations and etc. In particular, for Alluxio, we use 3 copies for every data file. And we are not using any memory. We're using hard disk for caching, which is presumably the worst case for Alluxio. And we tried some workload to do the comparison. So as you can see here, with different workloads, we can observe consistently better performance in Alluxio, 3 times better performance in Alluxio compared with HDFS. So to conclude this talk, I hope to make 3 points. First is in the new cloud age, the old way of doing DevOps is breaking. So if we choose the wrong technology, your data team could end up spending 20% of the time doing dev and 80% time doing ops. So resolving alerts every day is not fun. So this has a very big impact on CapEx and OpEx. And if your engineers are not happy, they will find another job. As simple as that. So there's a very high cost in the human resource expense, which is often ignored by other technologists. So in the cloud age, we want to put an emphasis on automation. So we try to automatically deploy everything, including applications and platforms, all the components. We want to automatically scale all those systems, and we also want to do automatic failure recovery. With all this kind of automation in place, it will be possible to accomplish 90% time doing dev and with 10% of time doing ops. Dropping ops time to 0% may not be realistic, but a 10% I think is achievable and will be very nice to your business. So in order to make this happen, we advocate adoption of cloud-native technologies. For example, we can do everything, treat everything as code, not just software, but also configurations. We have heard about infrastructure as code, but I think the same paradigm could be generalized to include platforms and applications as well. And from the 2 examples I've given so far, we can see the benefits of introducing configuration orchestration, in which all the configurations are automatically generated. We have seen impact of this, which reduced daily alerts from 1,000 to 20 every day. And the second example, we see the benefits of introducing data orchestration, in which, for example, Alluxio provides transparent, intelligent caching and a unified address space, which helps simplify the architecture and can fundamentally reduce the cost on operation. Thank you. That's the end of my talk.